All right, guys. So it's been a bit. Hopefully things are still in there somewhere. But last time we kind of talked, we finished up the kind of the MEKF story last time by talking a bit about star trackers and kind of how those fit into the model um, in the MEKF. And the essential idea is that because star trackers kind of natively give you an attitude quaternion, you basically kind of have to do the multiplicative stuff in the innovation now in the like sensor update part. And sort of saw some example code on that stuff, and now you get to implement it in the homework. Um, and I think that roughly does it for attitude determination stuff. And there's going to be a little bit more on the homework. Maybe next week we'll do some gyro stuff and that'll kind of feed into it. But I think roughly speaking, this is kind of wrapping up the attitude determination stuff. And we're going to start shifting into um, more control oriented stuff. And but today we're going to sort of ease into that by first talking about sort of why we do control to begin with, which is kind of environmental disturbances. So environmental torques on the spacecraft. And usually the reason for the control system is that there's weird stuff going on in the environment, perturbing us, knocking us away from where we want to be. And we need to kind of cancel those out, counteract them, et cetera, with feedback. And so we'll start talking about that. And then hopefully, like we'll get through a little bit of that. And then we'll talk about first some like fun, kind of old school, but still used in the small sat end of things, kind of techniques for passive attitude stabilization. And so, because it kind of naturally fits into this environmental torques discussion, today we'll get through that, and then we'll hopefully talk about gravity gradient stabilization, which is a fun way of making your satellite do nadir pointing sort of for free, which is cool. Has anyone heard of this before? A little bit. All right, cool. Talk about it. It is a classic thing that was used in the early 60s and has since been sort of resurrected in the small sat era as a quick and dirty way to get CubeSats to do nadir pointing without having complicated onboard control. So still used and still kind of relevant. Okay. Any questions about anything at all? We get into it. Okay. So let's talk about environmental stuff a bit. So this will be, I think, none of these are super surprising, but I think let's try to like enumerate, disturbance torques from the environment on the spacecraft. So anyone have any? Want to try throw some of these out?
Drag.
Yeah, so drag's a good one, and we kind of already hinted at some of the homework. Let's talk about that a bit. Okay, so in terms of modeling drag, so you guys had to do kind of surface area calculations and normal vector calculations. So that's how you kind of like add up these things. But where they actually come from, um, ultimately is from the atmosphere. So it's worth talking a bit about that. Atmospheric density. Does anyone know sort of what the atmosphere looks like up in low Earth orbit, like in terms of density and how it kind of scales with altitude? All right, so it turns out it's pretty easy to do some really rough physics calculations and get like a first order ODE for this. But atmospheric density sort of scales exponentially as you go up. And what that means is it changes dramatically as a function of altitude. It also changes dramatically as a function of things like season, day, night, because of this exponential dependence. It can vary by like a couple of orders of magnitude in a relatively narrow altitude band. So that's all kind of worth knowing. Um, and a good first approximation is an exponential. You can always kind of locally fit an exponential over some altitude band. It's more complicated sort of globally, but this is a good kind of um, rough like local approximation that you could fit typically. So here's kind of a classic way this looks. So if where h would be kind of my height above the ground level. So it'd be if you're talking about orbital radius vector altitude, you got to subtract off the radius of the Earth in here, but um, you kind of have something that looks like this. where this thing in the exponential is called the scale height, which is sort of like a, like a 1 over E type constant for how quickly the atmosphere varies. And then this H is just the height above like sea level or something. So this is a good first approximation. Works well over like a, say 50 kilometer, 100 kilometer altitude range. You can fit these for kind of use in GNC loops. What we actually do in practice a lot of the time is assume a model like this and then go fit the parameters. So we go fit the rho naught and the H online to data, like in a Kalman filter or something like that, to get a better estimate. And then there's kind of, you can get more accurate and fancy. So there are many atmosphere models. Has anyone heard of any of the kind of standard um, atmosphere models that are used for like orbit propagation? There's a few standard. Harris-Priestler is like an old school one that shows up a lot in satellite dynamic stuff. There's a MISSI model. There's a few of these. But yeah, those things account for things like temperature, variations, seasons, solar cycle, all kinds of things. One, I think, general message here is that because of that exponential dependence, it varies by a huge amount, and it's actually really hard to predict. And so, like, all these atmosphere models are actually pretty bad in practice, and they can be off by factors of like 2 or 3 very easily. So, takeaway message from this is usually what you want to do in a GNC context, if you actually care about predicting orbits and things like that accurately, is assume like a local model like this and just fit the parameters to data and basically estimate the local density online or some proxy for that. And then anyone know where this matters in terms of altitudes, like orbital altitudes? What do we think? Like where do you have to stop worrying about drag basically in terms of orbit propagation and torques? I don't have any idea. So yeah, that's about right. So 500-600 kilometers is kind of the where, because remember it tails off exponentially. So it tails off really quickly as a function of altitude. And interestingly, 600 kilometers is traditionally considered like this kind of vague cutoff for where you kind of stop worrying about drag and start worrying about other effects. And the gist is at about 600 kilometers, drag and the next biggest. So when you're below about 600 kilometers, drag is the dominant perturbation. It dominates over everything else except sort of two-body gravity kind of effects. Once you kind of get above 600 and this tails off, then other effects start to matter about as much. And that's kind of considered this kind of crossover point. Um, so yeah, that's pretty good. So Earth orbits below, let's say, um, 500 or 600 kilometers altitude. Okay, so that's kind of, I think, enough about drag. You know how to kind of calculate this, and you have the simulation infrastructure to kind of deal with this now. Other stuff. What else should we worry about? SRP. Okay, so yeah, so that's a good one. So SRP, for those not familiar with the lingo, is solar radiation pressure. This is kind of fun and interesting. So everybody's probably heard of solar sailing and stuff like this, right? And the I guess, okay, first question is, how does this scale as like a function? So it's coming from the sun. How does the like magnitude of this scale with distance from the sun? To get farther away from the sun, this obviously should decrease. So any thoughts on like how it scales as a function of like distance from the sun? Why? So that's exactly the right intuition, but that's exactly where the inverse square law comes from. And the reason is, as you go out, so this depends on surface area. So like if you think about a solar sail, the amount of flux on the solar sail goes like area. And so literally like flux is in like watts per meter squared, right? It's an area thing. So as you go out from a point source, like and expand out as a sphere, the surface area of that sphere goes like r squared. So I don't know, fun fact. So tons of stuff like gravity, sound, amplitude, solar radiation pressure, like almost everything that kind of comes out as some kind of field scales like 1 over r squared. And it's because of this like super dumb geometric picture of like expanding sphere from a point source, and it's the area of the sphere. Basically, if you imagine some amount of energy is released and it goes out in like a spherical shell from a point source, the area gets spread out on those like r squared, right? So that's where that comes from. So this scale like 1 over r squared from the sun. So this is like r's distance, the sun. Isaac Newton figured that inverse square law thing out. That was kind of the original gravity thing, but it's kind of everything. And then yeah, this is kind of fun, weird physics stuff. So people have looked at like photon pressure before. This is actually like a, I don't know, weird like relativistic kind of quantum-y thing. But it's straightforward to calculate and I think pretty intuitive. So if you think about um, the momentum coming from like a photon, so we'll call this P photon, where this P means momentum. It's the physics letter for linear momentum. It turns out this goes like, oops, this goes like E, where E is energy over C, speed of light. And so yeah, photons carry momentum even though they don't have any mass, which is a weird thing. So that's momentum. So if we think about what is force, if I want to go from think about force related to momentum, force is the time derivative of momentum, right? So if I just take this and then differentiate with respect to t, so I get something like the force from one of these guys then is just E dot. So that's time derivative of energy. What's time derivative of energy in like units or whatever? So time derivative of energy is power, which has units of watts, right? So that's like force. And so then if I want pressure, oh yeah, this is terrible. I got P's for both things. This is awful. Sorry. Should have thought about this more. Bad notation. Bad Zach. We'll overload. Maybe I'll should use a different letter. Okay, so this, if we're talking now pressure, horrible, horrible. Pressure is force per unit area, right? And now we're basically going to think about, okay, so force per unit area. So now I'm just taking that force thing and dividing it by some surface area. So we're going to get some kind of like constant fudge factor out front. And then we're going to get E dot, which we're going to call W, which is power over speed of light. So this W is solar flux. And this is bad. Sorry. I'm embarrassed. Usually I do better at that. So now we got force per unit area. This is solar flux, which has units of watts per meter squared. And then yeah, C is speed of light. I should write that. This is like a hand wavy sort of derivation of like how you get here from just like kind of the momentum of a photon. And let's see what else. This thing out front is sort of a fudge factor constant that's basically reflectivity. And it varies from 1 to 2. And the idea here is 1 corresponds to like basically absorbing the photon. So you just like wax into you and the momentum of the photon gets absorbed by the object. 2 corresponds to perfect reflection. So it's going to basically like perfectly elastically bounce and bounce back. And that's going to now impart double the momentum, right? So everything has some reflectivity between those 2 extremes. So if it perfectly absorbs, boom, that's it. You get the photon momentum. If it perfectly reflects, you get double the photon momentum. Most surfaces are going to be somewhere in the middle. Yeah. Okay. Does anyone know what like solar flux is? uh, around the Earth and the sun. It's a good random factoid. I don't know. You do this enough, you remember it. It's also how you calculate things like solar panel power, things like this. So at Earth orbit, so like at 1 AU from the sun, the solar flux is about 1,360 watts per meter squared. That's 1 AU from the sun. And if you need to figure it out anywhere else in the solar system, you literally just scale that like inverse square. So like 1 over r squared, starting at this is 1 AU. So if you go 2 AU out, it's going to be a quarter of that, right? Makes sense? Okay. So then if I take that number and sort of turn it into a pressure via this calculation, like divide by speed of light, whatever, um, this tells me that this is a roughly, just to kind of like get magnitudes in your head. I take this and sort of divide it by speed of light, which is like 3 times 10 to the eighth meter per second. This is about 4.5 micro pascals. So not huge, but like it is measurable. It makes a difference. And the back to that like 600 kilometer number, 600 kilometers is about where drag and solar pressure break even, to where they're about the same. So that's kind of where that number comes from. So below about 600 kilometers, drag completely dominates, and like solar pressure doesn't, relatively speaking, doesn't matter very much. Fun fact, to make a solar sail work and not just be a drag sail, you got to be above sort of this kind of 600 kilometer-ish number. And annoyingly, many of the solar sailing demos that have been flown on small sats have been below 600 kilometers. So really just drag sails. Fun fact. Not to knock those people. Like that's the deployment and attitude control of those things is very hard. So like they're getting at some important stuff, but they didn't really necessarily do solar sailing. So you got to be above about 600 kilometers for this to kind of really matter much. Okay. So far we got drag, solar radiation pressure. Any other ideas? What else we need to worry about? No.
The body forces.
Not so much, it turns out. Like they're pretty, so we'll talk about gravity stuff, but yeah, it turns out those are super tiny with regard to like attitude torques, that they're basically never relevant. Uh, Maybe if you were like in a very crazy, like, I don't know, like Saturnian moon situation where you had like pretty extreme kind of like third body effects and like tidal forces, maybe it would matter in that context. But I've never seen it matter in like uh, from an attitude dynamics perspective. Did you have something before? Or were you gonna say solar radiation pressure? Yeah. Okay, there's some other stuff. You're not, there is gravitational stuff that matters. Just not really the third body thing. Yes, 100%. That was next on the list. So okay, cool. So let's see, let's talk about this one. So obviously planetary magnetic fields are a thing. And they exert torques, right? So magnetic field, if you have a like dipole, there's sort of, M cross B, there's these kind of torques. So these exert torques on spacecraft that have a magnetic moment. which can be due to a whole bunch of things. So it could be due to sort of the obvious case would be like permanent magnetization, like you have a permanent magnet. Or if you have any kind of current flow, you're going to generate magnetic fields, right? There's also very weird effects that happen. It's because there's like, these effects are all small, but because, space is like a super clean environment generally, and there's no like other damping effects, like these small environmental effects actually integrate up over time and start to matter. So very weird stuff can happen. So for instance, we have like on-orbit experiments with small sats that we like spin up, just gradually spinning down over time for no other explainable reason. So there's no external torques otherwise. Like it's CubeSat, you spin it up, you leave it alone for a couple of weeks, and it gradually spins down and stops spinning. Like why? What could possibly do that? Like it can't be from any internal flexible stuff because that's all internal. Angular momentum is conserved. There's got to be some external torque acting on the spacecraft. And it turns out like the only real explanation for it is magnetic field interactions. And there are weird effects that happen, such as like eddy current interactions. It turns out any conductive surface that interacts with a time varying magnetic field um, forms little current loops in the metal. So even if it's not a ferromagnetic material like aluminum, that can cause effectively magnetic braking. So this eddy current braking effect is actually used in engineering applications. It's how they do braking on roller coasters, it turns out. But these can be exploited in space contexts, and you can get eddy current damping due to like not even having like ferromagnetic materials, just conductive materials, just like aluminum, which can like cause long-term sort of spin down effects. So weird stuff happens that turns out to matter. So magnetic interactions, kind of complicated. Okay, so how do these scale? It turns out you were right on the R cubed on this one. It's not, so magnetic fields, it turns out, scale like R cubed. Um, where that's sort of distance from the planet. So this is like a good thing and a bad thing. It's a good thing from like a sensor perspective. So if you care about doing like, for instance, good magnetic field measurements, so you want to have like a magnetometer on your spacecraft. This 1/r² R cubed helps you because it's a pretty steep exponent. So things fall off pretty quickly when you go away from some magnetic source. So if you care about really good magnetic field measurements, you don't have to get very far away from the spacecraft bus before this tails off quite a lot, and you get relatively clean measurements from magnetometer. So a standard move um, to get clean magnetic field measurements on spacecraft is to stick the magnetometer out on a boom a few meters from the bus. It turns out you don't have to go that far for this R cube to really help you with the kind of noise from the bus getting sort of knocked down several orders of magnitude. It hurts you in the sense that like as you go farther away from the Earth, if you're trying to use the magnetic field for actuation, which we're going to talk about, it tapers off pretty quickly. So it's very useful in low Earth orbit, but it gets harder and harder to use as you go to higher orbits. Okay, yeah, so just said this. This does definitely do stuff in the passive dynamics, but mostly when we talk about it in the spacecraft context, it's to use it for actuation. And this is via devices called magnetic torque coils, which are just electromagnets. So these are like literally just coils of wire. You run a current through the coil, you generate a magnetic moment, it's an electromagnet, and then you get an interaction between the local magnetic moment that you're generating on the spacecraft and the Earth's ambient magnetic field that can generate torques. And you can use that to do attitude control. It turns out it's sort of complicated. And our group's done a ton of stuff with this, trying to like do fancy versions of this to do three-axis pointing and things like this. Historically, they're mostly used for what's called momentum dumping. So you have reaction wheels, you have other stuff going on, and you just use the torque coils to offload angular momentum from your wheels instead of having to use thrusters to save propellant. Let's see, this can be used sort of from low Earth orbit kind of up to geo, and then sort of not so useful after that. Okay. So that's about it for the magnetic field stuff. Thoughts, questions on that? All right. So there's sort of one big one left that we didn't talk about. Yeah.
J2.
No. So it turns out, so J2 is going to, do things to the orbit for sure. But that's kind of generating forces at the point mass level. So we're looking for something a little different, that's going to generate torques. This one's weird, and maybe no one's heard of this. Okay. So turns out there's this effect called the gravity gradient torque. Has anyone heard of this before? No. Okay, gravity gradient. So we're going to talk about that. This one is also fun and not super obvious until once you hear about it, it's sort of obvious, but this one's also something you can use and exploit for passive, like old school attitude stabilization. Okay, so we all know, or we're just reminded that gravity goes like 1/r² with distance, right? So that's the first fact that we need. And so as a result, if I have a big, like, let's think about a big dumbbell satellite. So it's long and it's like, just say for sake of argument, it's like a dumbbell with two big masses. And let's say those masses are, let's say it's rotated such that like the masses are at slightly different altitudes. Those two masses will feel different gravitational forces as a result, right? So the lower one feels more gravity than the higher one, right? And so that's going to generate a torque. This one's going to get tugged more than this one, and it's naturally going to want to pull the dumbbell so that the long axis lines up with like the nadir vector, the radial vector. So the long skinny axis is going to want to point towards the center of the Earth as it goes around the Earth, and you get this kind of what's called gravity gradient torque. So as I just described it there, it should be kind of obvious that like if you do it right, you get this natural restoring torque in that long skinny orientation, and that can be stable. So you can get essentially like a stable pendulum mode for a dumbbell oriented with the long axis along the radial direction. So let's write this down and draw a picture. Okay, so say we got our Earth down here with our standard gravitational parameter mu. And then let's say we've got our satellite up here with like our dumbbell satellites. We've got two M's. So we got like an M1 and an M2. And then we've got two different like radius vectors, right? We've got, let's say, R1 and R2, where R2 is bigger than R1, right? So as a result, we're going to get two different forces. So the gravity on mass one goes like 1/r1². And then the force on the second one is going to go like R2². F1's bigger. So we've got something like sort of R2 is bigger than R1, which tells us that F1 is going to be bigger than F2. And sort of as we are saying, this is now going to generate a torque, and it tends to align the long skinny axis in the radial direction. And then, as I kind of already said, you can use this to stabilize an Earth pointing, like nadir pointing spacecraft. The only catch being you have to get the mass distribution to basically look like a dumbbell. So in practice, the way this is done is by deploying a long boom with a mass on the end to make the thing look like a dumbbell. And there's a long history of doing this. Actually, we talked about the transit satellites before that were like kind of the first navigation satellites that also were the first satellites to do attitude determination with like to triad algorithm. They were also one of the first satellites to be nadir pointed using gravity gradient. So they had gravity gradient booms that they deployed on those transit satellites to get them to point down. Okay. Any questions about this? So one thing to, so yeah,
This the same as like time to block.
yeah, this is basically the same as a tidal. This is basically the satellite version of like a tidal effect or tidal locking for a moon or an asteroid. Yeah, same idea. Yeah, yeah.
It's the same thing that happens like when you're falling on black hole, your body gets like stretched out, right? It's like
Yes, it is. It is the spaghettification. It is the much milder sort of classical version of the spaghettification phenomenon. Has anyone heard about this? It's like this classic kind of thing about black holes where there the gravity's so strong that the gravity gradient effects are so strong that like if you were to sort of go down one, you'd be stretched because of the force, the gravity on your head versus the gravity on your feet. The difference is so huge that you would get stretched, like into spaghetti. It's a classic kind of like GR thought experiment thing. So it is the same thing. Yes, that's exactly right. Yeah. This is a much milder version of these effects, but it's the same idea as tidal locking and yeah, that. Okay. Any other fun things to think about? So one thing that's worth mentioning is this effect. So even though you might model like kind of J2 and higher order gravity effects when you're doing orbit propagation, it turns out this effect is like already pretty small, such that like we really only worry about the spherical term when we do gravity gradient. Like the J2 term is so small that it doesn't matter. It's like many orders of magnitude down. So generally just worry about this. Okay. Anything before we keep moving? All right. So what we're going to do now then is we're going to keep on the gravity gradient theme because it's fun and talk a little bit more about that. So first thing we're going to do is sort of derive the torque due to gravity gradient. It's kind of cool, I think, little trick. And then we'll talk about gravity gradient stabilization, like how you can engineer this into a satellite, which is a good trick. It's still used actually pretty frequently by CubeSats because and on the CubeSat thing, typically you do the classic tape measure, Stanley tape measure trick to make the boom happen. So you can roll up a tape measure, stick a mass on the end of the tape measure, tie it down, and then to deploy it, you deploy it with a burn wire, unroll the tape measure with the mass on the end, and there's your gravity gradient boom. Basically to first order, all deployables on CubeSats are made out of Stanley tape measure. It's a fun fact. So much so that the paint on Stanley tape measures is in the NASA outgassing database. It has been officially tested and approved by NASA. All right, so gravity gradient torque. So we just talked about what this is. So we're going to try to like actually be a little bit rigorous about it and show you how to calculate it so that you can stick it in your simulation code. All right, so if we kind of think now, instead of a point mass, we're thinking about a general rigid body, satellite, and a gravity field. So we've got our planet somewhere over here. It's got, two-body gravity with a gravitational constant mu. Then we've got our like potato satellite up here with a weird mass distribution with some centered mass. All right, so the way we're going to write this down is we've got a vector to the center, from the center of the Earth to the center of the satellite that we're going to call R naught. Then we've got another set of vectors from the center of mass of the satellite to like each point of mass in the rigid body. So we're going to call those R sub i's. And then like each little mass element is an M sub I, right? So I'm doing this like kind of hand wavy, assuming a discrete sum. In general, it's be an integral, whatever. You can discretize it as finely as you want and get the right answer. So we're going to have a situation where we have like the total mass of the satellite is going to be some sum from I equals 1 to n particles of these mi's. And then we've got these little ri's to each little mass spec, right, in the satellite. And the big important message here is that the R naught here, so the vector from the center of the Earth to the satellite, is much bigger than these ri's, right? Than like the size of the satellite, or so for instance, like this might be order like 10 to the sixth like meters. And then these RIs might be sort of like order 1 meter, right? So they're like a difference of like 6 orders of magnitude. This is important because we're going to use like a Taylor expansion argument to figure this out. Okay, so now if we write down the gravity, the force due to gravity on this thing, we're going to just sum over all the little mass specks in this guy. And they're just like, 1 over r squared. So it's mu minus mu times mi for each little mass over, then the distance from the center of the Earth to each mass is going to be r naught plus ri. And then we're going to cube this and write down, the vector over here. Cool. So I'm just like summing over each little piece of mass in the satellite and like adding up the gravitational force on each little piece of mass. Okay, so that's sort of the general thing. And the argument we're going to make here is that since the R naught is way, way bigger than the Ri, we're going to Taylor expand that gravitational force to first order about R naught. And that's the cool thing here is because that's like 6 orders of magnitude difference. This is for a typical satellite. This is essentially exact. Even though I'm doing the Taylor expansion, it's for all practical purposes the exact answer, right? It's good like 6 significant digits. So we just call this the gravity gradient torque. So there's that. Taylor expand about the R naught. The first order approximation will be good to about 6 significant digits. So it's essentially exact for us. Okay, so the like cartoon version of this that we're going to do. So the cartoon, I think, should be clear. So we've got this like force as a function of r, and it's going to be approximately sort of just the force computed about r naught. So if I just lump it all into a point mass, that's it, plus some sum over these little masses. That's sort of, I'm just going to take the Jacobian df dr evaluated at r naught times the ri's. All right, so this is, the nominal point mass force at center of mass. And this is basically like kind of tiny, tiny adjustments due to finite mass distribution, due to the fact that this thing is not a point mass, that it has some actual finite extent. So that, hopefully that's clear. That's the recipe. I think that's the important thing. And then the rest here is just like me doing some chain rule stuff and like isn't actually important. I think that's the important thing. It's just like now I'm going to derive that second term. Okay, so if I guess I'll just do it kind of quickly. I don't know. I feel like the matrix calculus stuff is it's a slog sometimes, but it's not that bad. Also, I feel like it's a useful thing to know how to do. When I had to learn this stuff, it was before like auto diffing was a thing. And I had to like hand do all this stuff and code it up in MATLAB. Now you have auto diffing, which is great. Okay, so that's what that thing looks like, right? Like the inverse square law thing. I'm writing it in a particular way to like let me do calculus stuff. So this is just 1 over r cubed, but I've squared it and then taken a 3/2 root to make it r cubed. And then I've got the r on the outside. just going to do like normal sort of product rule, chain rule stuff. So I'll just write you down the answer and then you can chew on it if you want a little bit. So first what I'm going to do, so there's kind of like two sets of R's in here. There's this one and then there's these ones. So first thing I'm going to do is I'm going to take the derivative with respect to this R because that's the easy one. And then I just literally I just pull that R off and I stick an identity there. So that's the first term. Okay, so that's the derivative with respect to this R. Now I have to take the derivative with respect to these downstairs R's, which is a little bit more annoying, but it's like not hard. Um, here's what it looks like. Shouldn't be a huge surprise. Okay, so I don't know. Is it worth talking about how you do this stuff, or are you guys just gonna like throw it out and I think it doesn't matter anymore? I don't know. But yeah, so this is like, this to the minus 3/2. So then I get a, you know, minus sign. That's why that's a plus, a 3, and then I get a 5/2 on the exponent. Then I also get like a 2 from this guy that's like squared. And that cancels out the 1/2 from this exponent. So that's where that comes from. And then the derivative of this guy is R transpose. So that goes over here, and I have this R to begin with. That's like the whole thing. So I don't know. This stuff's weird. No one really teaches you how to do this, unfortunately, which is annoying. I think this should be taught, like how to do matrix vector calculus stuff. That's how you do it. If you do it enough, it becomes sort of second nature. And like the rules make sense and they're mostly the same as freshman calculus, but there's like stuff to be careful with transposes and stuff. I don't know. I think it's useful. So this is the thing we're after. And we'll call this sort of the gravity. Oh, what the hell? Why did you not? Okay, we're going to call this thing the sort of gravity gradient, like Jacobian. So this literally is the gravity gradient, right? I just took the gradient of the gravitational force with respect to R, but it's not really a gradient because it's with respect to a vector, so it's really a Jacobian matrix. But we're going to hand wavily call it the gravity gradient. It really should be the gravity Jacobian. Okay, whatever. Splitting hairs. So that's that. So now we have the gravity gradient like force, and now we're just going to take that and do like the R cross F, torque calculation with that thing. All right, so torque, no surprises. We're going to sum over our little mass particles, and it's just Ri cross Fi. And we're gonna, we could literally take it and plug it into, this sum up here. But instead, what I'm going to do is take it and plug in this first order Taylor expansion, right? So this is going to look like something. We got our R cross, and then I'm just going to plug that mess in to this evaluated at R naught, right? Cool. Simple enough. Okay, so that's it. Then the rest of this is basically kind of like massaging this a little bit, but something cool happens. So I'll like maybe tease what happens slightly. So there's a couple of little tricks. The first trick is, if I stare at this for a second, this first term looks like Ri cross. This is a scalar, and then this is just Ri over here, right? So what does this first term look like inside the sum? So it's like an Ri cross Ri, like a scalar. So it's Ri crossed itself. So this first term drops out and does nothing, and only the second term sticks around. So that's like the first fun fact. So we can do that. And then the other thing that you can start to do, so I guess we'll do that first. So that term's going to drop out. Maybe I'll write this down. Then down here, we're going to get, so we just have this term now. All right, so what I did here is I just pulled this constant out front and the stuff inside is, the same stuff. Then the next trick is I'm just going to flip the ordering on some stuff. I'm going to try to, so the R naughts are constant and the RIs are what we're summing over, those little masses. So I'm going to sort of flip things around to pull the R naughts out because they're constants and put the RI stuff inside the sum. And that's going to make this look like so. And yeah, basically I can pull the R naughts out and sum over this stuff, right? Okay, so that's like all kind of still weird and messy. Now is the fun trick, which is if we recall the definition of the inertia matrix from a while ago, one way to write it is like this. Oh, and if I like stare at this for a sec, um, this term is basically this term from the inertia matrix. And if I go ahead and plug the inertia matrix in there, this term, which is like scalar times identity, is going to get you another sort of R naught cross R naught. Like it's going to cancel out because of the cross product with itself argument again. So I can take the sum and just stick the inertia matrix in there, which is pretty slick. So which kind of makes sense in some hand wavy sense that like ultimately the inertia matrix is capturing the mass distribution sort of up to second order. So in some Taylor expansion-y kind of way, like it makes sense that I should be able to take whatever mass distribution terms are showing up in this sum that I've Taylor expanded to first order. I should be able to take that and replace it with an inertia matrix because that's kind of what the inertia matrix is. It's like a kind of rough approximation of the mass distribution or representation of it. So that's what we're doing. And so like just I guess to summarize why we can do this term will cancel out. For the same reason as before, do this cross product itself. So then after all this, we're going to end up with something that looks like this. Um, okay. And that gets a box. And this is what we call the gravity gradient. Torque. Uh, okay, yeah. Summarizing, we did a first order Taylor expansion to get here, but it's okay because it's like essentially exact for like normal size satellites that are much, much smaller than the orbital radius. It's good to like, as many decimal places as you could really possibly care about. And yeah, there's this nice little trick where the inertia matrix pops in there over instead of the sums over the masses. Quick question now. How does this thing scale as a function of like distance from the center of the Earth? So gravity goes like 1 over r squared. We know that. Magnetic field goes like 1 over r cubed. How does this thing scale? It's like not immediately obvious. You have to stare at it for a second to figure this out. It's not that hard. Yeah,
It's just one rock.
not quite. Okay, so this is like 1 over r squared to the 5/2. So this is 1 over r to the 5th. And then this is r squared over here. So this whole thing goes like 1 over r cubed. There's a bunch of vector stuff in there, which is like not obvious, but yeah. So that's worth, I don't know, knowing. Oh, weird. Damn it. I feel like these like order of magnitude kind of things to have in your back pocket are really helpful. I don't know, for like rough order of magnitude calculations. Okay, and now next question is, um, so okay, we have the inertia matrix in there. This R is like the orbital position vector, basically. Um, when is this 0? When will there be no gravity gradient torque on the spacecraft? So not necessarily identity, but what do you need to be true about that thing?
Particular.
Parallel.
Yeah.
Yeah, it's cross product is 0 when the vectors are parallel, right? So these things need to be parallel to each other. When are they going to be parallel? It's the same as the Euler's equation stuff. So I need R to be parallel to J times R. When is J times R parallel to R? It's the definition of an eigenvector. Eigenvector is when you multiply the vector by a matrix and you get the same vector out, just maybe scaled, right? Okay, so if R is an eigenvector of the inertia, then what comes out of this is just going to be a scalar times R. That's definition, right? It's like literally AX equals lambda X, right? Okay, so if R is an eigenvector of the mass matrix, the inertia matrix, then this will be parallel to this, and this thing will come out to 0 because of the cross product, right? It's the exact same argument as the Euler's equation thing for the equilibria of a spinning rigid body. So this is saying that when a principal axis of the inertia is lined up with the radial vector for the orbit, i.e., what we were talking about before, the dumbbell, the long skinny axis. So one of the symmetry axes has to be lined up with the orbital radius vector, i.e., has to be like pointed nadir down the radial direction, right? In principle, from this, any of the symmetry axes, any of the principal axes could be aligned with the radial vector, and you'll get 0 torque, but not all of them are stable, sort of like the Euler equation situation. Does everyone see that? Makes sense? It's the same argument as before. Uh, okay, so let's write that down. All right, so whenever, yeah, inertia principal axis is sort of lined up with the radial direction. And then the last note on this is, so we did all this with some low order approximation stuff. And I'm just going to say, like, it's usually sufficient to ignore higher order gravity terms like J2 when you calculate this, because it's already like kind of a small thing. Okay. Hopefully that was fun and interesting. Uh, let's see. So we got like 20 minutes or so. Um, let's talk a little about the gravity gradient like stabilization trick and like kind of vaguely what that looks like. I'll try to like give you the cartoon picture without like bogging us down in like the math details so much. Um, so to talk about that, the first thing I'm going to talk about is this so-called like orbital reference frame or RTN frame. Has anyone heard of this before? Bunch of people. Cool. Uh, so this is sort of when we're talking about attitude of a nadir pointing satellite's trying to point at the ground. This is kind of the reference frame that's most convenient or natural. This shows up a lot actually. So it works. It shows up in like Earth observation kind of stuff. It also shows up a lot in sort of rendezvous and proxops, where you think about like, has anyone seen the CW equations? So those are also written in this kind of RTN frame. So it's a frame that moves along with the satellite in orbit. And there's a bunch of conventions for these and like different definitions of the coordinate frame, but a common one that I think makes sense um, is called RTN frame. And this stands for, I guess let me draw the picture. So let's say we have Earth, we have our orbit over here. Well, for now, we'll just assume a circular orbit to make life easy for now. So we have our sort of state vector. So this is like our R naught. And then we're going to define a set of unit vectors from here that are going to be the radial unit vector. So that just points in that R direction. So this we'll call this R. The tangential uh, unit vector, so that's T, and that just points in the velocity direction for the satellite. And then the normal vector, which we define to be the cross product of these guys. So I don't know, maybe I'll try drawing it like this. And so these are radial tangential, and that's parallel to the velocity vector. And then N, which is normal to the orbit plane. And these are defined such that N is R cross T to give you a right-handed coordinate frame. People seen this before? Maybe most of you. Okay, so important thing to note is this is not an inertial reference frame. It's a rotating reference frame by construction, which is what we want in this case. It rotates once per orbit. About the n vector, right? And let's see, for a circular orbit, just kind of what we'll assume for now to make things simple. Uh, the rotation rate is constant, and it's the mean motion for those who know orbit stuff. And we'll call that omega n. And we're going to kind of, to get at this, right? This sort of naturally in this frame to do nadir pointing basically means we want the satellite axis lined up with this radial vector. So that's convenient. So we're going to write like all the kind of dynamics down in this RTN frame. Okay, so we just saw the gravity gradient thing. What we can do now is simplify it just slightly. So we had, just before we had this expression 3 mu over r. So this is what we had before. From the definition, if you like, not important here, but like from like basic orbit mechanics, just the definition of that mean motion. Just kind of the angular rate at which this frame is rotating around. That can be written like this, so that omega n squared is mu over a cubed. Probably people have seen this before. And for in our kind of notation with r naught, that is r naught transpose r naught to the 3 halves. So this a here, if you're not familiar, is the semi-major axis of the orbit, which in the case of a circular orbit, just the radius vector of the orbit. And that's what that is, right? So it's a cubed. Cool. So what we're going to do is just plug this mean motion thing in to our gravity gradient torque and replace that kind of nasty thing out front with this slightly cleaner thing. I messed this up. I did mess this up. No, I didn't. Okay, so now we've got this is like slightly tricky. So what we're doing here is up there it's r naught, which is the vector to the sort of from the center of the Earth to the spacecraft. Here, what I've done is I've written it as r, which is our RTN frame unit vector. So essentially what I've done is just like divide through by a couple times, and that's why this was a 3 halves, and that's how I get the 5 halves. Make that whole thing cancel. I went from r naught to r, so I've got like effectively another r naught squared that I pulled out, right? Okay. Let's see. And like we remember from before, right? This goes to 0 when r's parallel to an eigenvector or principal axis of j. And let's see what else is there to say about this. From the cartoon hand wavy picture, right? We know that like gravity gradient can provide a restoring torque. To sort of stabilize an Earth pointing satellite. Okay, so the question now is, I've kind of already hinted at this, like we know there's like 3-ish equilibria for this thing, for the 3 principal axes, but they're not all stable, just like in the kind of spinning rigid body Euler's equation setting. And what we want to do now is actually figure out how to make this thing stable. And the gist is you want to, in sort of an unsurprising way, and I'll foreshadow slightly, you basically want the long axis, the major axis, kind of the long dumbbell axis oriented in this radial direction. And to get there, like the recipe is kind of the same one we've done with the Euler equations to look at stability. We're going to write down Euler's equation with this stuff plugged in. Then we're going to sort of linearize about some nominal attitude and then check eigenvalues and make sure things are sort of pure imaginary and that there's no positive real parts that are going to blow up. It's the same recipe. And that's for those who haven't sort of taken linear systems courses and done a ton of um, this stuff is like super useful and shows up a lot. And that's like a very, very standard recipe for checking the stability of things, like local stability analysis, sort of linearize everything and check eigenvalues. It's extremely useful. So let's try to see how much as we can get through. I think the details aren't that important. I mostly want to show you like the general recipe and kind of the result. So we'll maybe go a little fast through this and skip some details. So what we're going to do is assume that we're sort of not in the nominal attitude that we want. So assume we're nominally rotating with the orbital frame doing what we want, but there's small perturbations. So the way we're going to think about that is, since we're talking about attitude, those perturbations are small rotations. So we're going to think about this as we've got some rotation matrix from the body frame to now, instead of the inertial frame, we're going to do this in the orbital frame. So we'll call that O. So everything's in this orbital frame, not the inertial frame. And so this thing, though, is we're going to assume that we're nominally aligned and that there's just small errors. So this rotation from the body frame to the orbital frame is approximately an identity plus a phi hat, which is just one of these. This is some phi axis angle thing, small rotation thing, and it's hatted. Remember, that's the first order Taylor expansion of the exponential that maps our axis angle thing into a rotation matrix. First order Taylor expansion is legit because phi is small. Okay, so that's the attitude, and now we're gonna look at the angular rate, the angular velocity. Um, so we have, remember, this frame is rotating, and it's nominally rotating about the n direction by this mean motion. So in the orbital frame, that's RTN, that's in the n direction. I'm going to rotate that from the orbital frame into the body frame. So that's like one contribution. And then the other contribution is due to my actual sort of perturbation stuff, which is just E dot. So the nominal rotation is just that like mean motion stuff. Again, rotating the body frame, which that Q thing is approximately identity. And then we've got like the velocity of the perturbations in there. This I can write using my Taylor expansion as I minus phi hat, because that's Q from O frame to B frame, whereas this is Q from B frame to O frame. So I flip the direction of rotation. I transpose Q. That's equivalent to picking up a minus sign here because I got skew symmetric. Transpose equals minus. All right, and this is the same. Okay. Well, so now if I kind of like expand that out a little bit, I can write omega in the body frame under my sort of like first order Taylor expansion kind of small perturbation assumption. In components, I can write it like this. So I've got phi1 dot minus phi2 omega n, phi2 dot plus phi1 omega n, and phi3 dot plus omega n. That's just from like actually taking that cross product out, writing it down. Okay, so this we're gonna hold on to. That's our omega. And now the recipe is I'm gonna like plug that omega in to Euler's equation.
So on the B is there.
Oh, sorry. That should be a 2 and a 1.
That's a B dot one minus B two.
That's phi dot 1. So the phi dot stuff should be clear, right? That's just phi dot. And then this stuff is coming from the cross product of like, this is minus phi cross of this guy, right? Okay, so that's omega. Now we're going to take um, this stuff and um, plug in, we're going to plug this and the gravity gradient torque into Euler's equation. And we're going to, like the recipe at a high level is plug this in to Euler's equation, plug in the gravity gradient torque into the right-hand side of Euler's equation. You get one sort of set of ODEs for the small angle perturbed attitude dynamics, Taylor expand, check eigenvalues. Like that's the whole game. So hopefully that high-level recipe is clear. The details I think are a lot less important. So maybe we'll like sketch it a little bit and then try to like mostly just show you the answer before we're out of time. Um, so maybe I'll just like kind of high level sketch. Okay, so and then we're going to assume sort of like we did before that J is diagonal. And that lets us kind of write all this stuff down cleanly into Euler's equation. Then we get kind of like three sets of equations, like the three scalar versions of Euler's equation. Um, so maybe I'll write those down real quick. We've got looks really similar to the stuff we had before when we did this. And, you know, kind of just in components, it's a little messy. So this is like Euler's equation in components, like we've seen before. And the omegas in here, those omegas with the subscripts, those are just coming straight out of here. And the taus on the right-hand side with the, you know, 1, 2, 3 components, those are coming straight from our definition of gravity gradient torque up here, right, from this guy. So like that's it. You just kind of write it in components, plug it in. And after doing a whole bunch of massaging, you'll get a couple of fun things. The n-axis motion, so like the third one, is actually really simple and kind of clean and easy to write down. That axis decouples and looks like a simple harmonic oscillator, like we've seen before. So this one looks relatively clean. You're going to get something that looks like this. So yeah, this is like classic simple harmonic oscillator. And then this ends up being your oscillation frequency, this thing out front, right? So this is omega 3 squared. And then like we saw before, for this thing to be stable, we need this thing to be like pure imaginary when we take a square root. And oops, to have that happen, similar to the Euler equation stuff we've already seen, we need J22 to be bigger than J11. Put a box on this guy. Okay, so that axis is easy and like relatively straightforward. What the hell just happened? The other two are complicated and messy, and I won't like drag you through the derivations of those. For those other two axes, it's coupled and a lot more complicated to get to the answer. If you care and you want to see it, it's in the Hughes book. That's one of the suggested reading references. They derive it out. You end up with this kind of crazy like sixth order polynomial that you have to solve for the roots of and blah, blah, blah. It's in the book. Book's on my desk if you want to check it out. Probably also find PDFs. But the end result is if I'll show you the plot, we're going to define a couple of constants that are functions of the inertias. So this is Kr. Again, like really similar to the Euler stuff we did before. So Kr and Kt, which are, radial and transverse kind of inertia things. And then in terms of these guys, you can express the stability of this thing. And I'll like drop it in here. And it looks like the following. Okay, so in terms of these Kr and Kt, so we already have this condition up here that J22's got to be bigger than J11. And then in terms of the other inertia elements, we define this Kr, Kt thing. And if I plot sort of stability in this Kr versus Kt plane, the white regions on this plot are stable. So you need the inertia to live in this area or this area. And then if it's in any of the color regions, it's got instability in one or more directions. So I didn't want to drag you through that. It's not that insightful, I feel like. But that's kind of the end result. So but if you pay attention to this, like the end answer is basically to make the satellite look like a dumbbell and line the dumbbell up with the radial direction. Cool. I think we're about at time.